Hi guys, I will explain tire pull from definition of PRAT and PRCF to graphs for Conicity and Ply Steer. Here I have a quiz for you. What is the correct description about A and B in a tire without camber? Number 1. A. Residual cornering force. B. Residual aligning torque. Number 2. A. Residual aligning torque. B. Residual cornering force. Let's define RAT, residual aligning torque, and RCF, residual cornering force. Since there is not only Ply Steer but also Conicity, I will use RAT and RCF instead of PRAT and PRCF. As shown in this figure, RAT is defined as the aligning moment corresponding to the slip angle at which the lateral force becomes zero. In addition, RCF is defined as the lateral force corresponding to the slip angle at which the aligning moment becomes zero. These two lines pass through the origin as shown in the dotted lines if there are no Ply Steer and no Conicity in a tire. Since the Conicity shows a behavior similar to camber, Ply Steer shows a behavior similar to steering, it is natural to try to represent the residual cornering force RCF using the camber stiffness and the lateral stiffness, and to represent the residual aligning moment RAT using the camber pneumatic trail and lateral force pneumatic trail and their corresponding stiffness. This idea is introduced in Hans Pazekar's book, Tire and Vehicle Dynamics, 3rd edition, page 193. As mentioned above, assuming that the lateral force Fy gamma due to conicity can be defined as a function of camber stiffness Cf gamma, the residual cornering force FRCF can be expressed as a function of camber stiffness Cf gamma and the equivalent camber angle gamma conicity. Furthermore, if the camber trail is applied to the equation for the aligning moment caused by conicity, the residual aligning torque due to conicity can be expressed as a function of camber torque stiffness Cm gamma and the equivalent camber angle gamma conicity as shown in this equation. These two figures came from the video number E18. I explained the cornering stiffness and the self-aligning moment stiffness. Both of stiffness are defined at zero origin. In the similar way, if the residual cornering force FRCF by Ply Steer is defined using the same stiffness value Cf alpha and the residual aligning moment MRAT is also defined using the same pneumatic trail T alpha, the equivalent side slip angle alpha ply by Ply Steer can be calculated. As explained in the previous video E0050, when the camber angle is 0, if delta 0 has a length other than a point on the side slip angle axis, it means that there is a conicity. Referring to the figure, the lateral force stiffness and the aligning moment stiffness can be expressed as a function of delta 0. Consequently, we end up with the expression RCF and RAT in terms of delta 0. Now let's look at the graph for a tire without camber, with Ply Steer, and with conicity measured from an arbitrary tire. we will develop the equation to calculate the equivalent camber and equivalent side slip angle about this figure. The given data are cornering force stiffness, self-aligning moment stiffness, camber stiffness, camber aligning moment stiffness, delta 0, and delta alpha 0. To derive the equations for equivalent camber and the side slip angle, let's first look into the tire having the camber without the ply steer and without conicity. Our first step is to calculate the lateral force Fy and the camber moment Mz due to camber corresponding to the side slip angle length delta 0. A lateral force Fy at the 0 side slip angle can be expressed as a sum of lateral force due to side slip angle alpha and due to camber angle gamma. Since the side slip angle equals 0 in the vertical axis, lateral force Fy can be expressed as this equation. In the similar way as before, we can calculate the aligning moment Mz at 0 side slip angle, which can be expressed as the sum of aligning moment due to side slip angle alpha and due to camber angle gamma. Since the side slip angle equals 0 here in the vertical axis, Mz can be expressed as this equation. We can get this figure if we describe the force and the moment altogether. We have a lateral force and the self-aligning moment at the 0 side slip angle in terms of camber angle gamma when there are no ply steer and no conicity. Now we are ready to derive the equation of camber angle gamma in terms of side slip angle length delta 0. Step 4 is represent delta 0 in terms of stiffness ratio and the camber angle gamma. Based upon what we calculated by now, we can calculate the length A and the length B using the trigonometry of yellow and orange right triangle. We can get the length A in terms of camber force CF gamma gamma and slope of Fy CF alpha. And we can also get the length B in terms of camber aligning moment Cm gamma gamma and the slope of Mz Cm alpha. Consequently, we can describe delta 0 in terms of stiffness ratios and the camber angle gamma. Step 5 is calculate the equivalent camber angle corresponding to delta 0. Now we can express the camber angle gamma in terms of delta 0 and the stiffness ratios. Gamma is equivalent camber angle corresponding to the side slip angle length delta 0. Left figure shows the case for camber only, and both ply steer and conicity equal to 0. A middle figure shows the case for camber equal to 0 and both ply steer and conicity not equal to 0. A middle one is the original figure given, which includes conicity component corresponding to delta 0 and the ply steer component corresponding to side slip angle alpha ply. We can get the middle figure when Fy and Mz move horizontally to the right as much as alpha ply. A right figure shows how to find the equivalent side slip angle alpha ply, which is the length difference between green and gray right triangles. The first way to calculate the equivalent side slip angle, alpha ply, is to find the difference of side slip angles. From the figure, alpha ply can be obtained by subtracting d from the delta alpha 0. On the other hand, from the right triangle trigonometry, d can be expressed as this equation. Consequently, we can obtain the equivalent side slip angle alpha ply in terms of delta alpha 0 and the stiffness ratios and the equivalent camber angle gamma. The second way to calculate the equivalent side slip angle alpha ply is to use the slope of force line. From the figure, lateral force Fy can be expressed as the sum of Fy alpha and Fy gamma. Therefore, the slope of force line Cf alpha can be expressed in terms of vertical component Fy and the horizontal component delta alpha 0. Multiplying both sides by delta alpha 0 and arranging the equation, we can obtain the equivalent side slip angle alpha ply in terms of delta alpha 0 and the stiffness ratios and the equivalent camber angle gamma. In this figure, let's learn how to read the graph of residual cornering force and residual aligning torque. Purple color represents the residual aligning torque at the slip angle at which the lateral force becomes 0. This is the moment preventing the vehicle from moving straight ahead. A driver should provide steering wheel with the opposite moment to move the vehicle straight ahead. Green color represents the residual cornering force at the side slip angle at which the self-aligning moment becomes 0. This force means lateral force with the steering wheel released. Let's take another example. In the same way, a purple color represents the residual aligning torque RAT at the slip angle at which the lateral force becomes 0. This is the moment preventing the vehicle from moving straight ahead. A driver should provide the steering wheel with the opposite moment to move a vehicle straight ahead. Green color represents the residual cornering force RCF at the slip angle at which the self-aligning moment becomes 0. This force becomes a lateral force with the steering wheel released. The answer to the quiz is number 2. A is residual aligning torque and B is residual cornering force. Here we have a summary. Residual aligning torque is defined as the aligning moment corresponding to the side slip angle at which the lateral force becomes 0. Residual cornering force is defined as the lateral force corresponding to the slip angle at which the aligning moment becomes 0. Conicity and Ply Steer can be expressed as the equivalent camber angle and the equivalent side slip angle. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E49, I explained the tire pattern blocks producing ply steer due to the same deformation behavior as that of asymmetric cross-section beams, in which the direction of displacement occurs perpendicular to the neutral axis and bring about ply steer. Recently, I explained the tire pull related to the pure conicity, pure ply steer, and their moving direction. The next video will be conicity and ply steer 25. I will explain the vehicle drift due to tire. Please hit the thumbs up and catch the brand new videos by pre-subscription. So, what are you waiting for? See you in next video. Goodbye guys!